upcoming events. Tamara's going to tell us about the Messier Marathon. Dana's going to tell us about the Dome Project. Brad's going to tell us about the Saros, is that how you say it? Saros cycle that they use to predict eclipses with. And then Byron Labadie has been to the dark side of the planet, down to the southern skies in Chile. He took a summer vacation in December to see the great telescopes down there in Chile. He's going to tell us all about that. So, next slide, Mr. Dan. There's our upcoming events. You can read them. We have our guest night at the observatory coming up the 11th, if it's not too cold. The weatherman was not being nice today. And then we have our members night on the 17th. Something comes after the 11th that I'm not too happy about, but if you read the newsletter, you know that daylight saving time starts. We need to write our local senator, Mr. Langford, because he's reintroduced the bill to get rid of standard time. Of course, if you like the sun not coming up from November 17th to February 23rd before 8 o'clock in the morning, I guess you'd be happy with that. But anyway, enough of my ranting. The Messier Marathon, I'll not steal Tamara's thunder on that. We're going to have some work days at the observatory, get everything spick and span for our Messier Marathon. And then we have some guest days in March also. So afterwards, before I forget, which is easy for me, I need a volunteer who has time to look through all of our newsletter feeds back to 2000. We launched a new website in July, and I discovered this weekend that some of the newsletters didn't transport over. I just click on them, see if they come up, and tell me which ones are up, and we'll see if we can't fix them. I've got a file of 7 to 8 years. Anyway, it just takes some time to see which ones are not working. So it's pretty easy, but just time consuming. All right, next slide. Volunteers. I've already mentioned our work day on the 1st. This is the one we had in March 17th, 2020, where we cleared out a lot of brush. I couldn't find the picture of the one we did last year on March 5th, where we cleaned up the inside of the observatory and spruced up the classroom. But there's a lot of things that need to be done out at the observatory. How many of you have been to the observatory? Most of you? You're not? You'd come out there to do that. But anyway, that's a work day coming up April the 1st. In June 9, 10, and 11, we're going to have guests from the 5-state region, mid-state region, coming to Tulsa here for a convention, plus all of us. And we've got some good guest speakers lined up. We're going to have a nice banquet and activities Friday evening, all day Saturday, banquet Saturday evening, and some more things on Sunday morning. So that'll be good. And we also have our guest nights at the observatory. I've been getting requests from schools and other places to have some telescope nights. So we always enjoy volunteers to come out, set up a telescope, and just help with the guests. All right, next slide. All right, we'll turn this over to the lovely Tamara Green. Up here, Tamara.
All right.
Try to get out of your way so they can see the other.
All right.
Sit down there where they can see you.
Okay. All right. For those of you who don't know me, my name is Tamara Green. I have been a member of this club for the better part of 20 years. I have held every office in this club except for treasurer, and I'm a current board member. And this year, I am coordinating the Messier Marathon. For those of you who are new to astronomy and don't know what a Messier Marathon is, I'm going to try to make this as quick as possible because I know there's other presentations tonight. But back in the 1700s in France, there was an astronomer named Charles Messier, and he was a comet hunter. And one thing that he enjoyed doing night after night was going out with his telescope, looking up at the sky and trying to pick out what he thought were comets. He saw these faint, fuzzy objects, naked eye, put his telescope on them to discover that they were not comets. A lot of them were galaxies, nebulas, star clusters, and he began to log these objects and their location in the sky so he would know not to look at them again. And now today, to make a long story short, the objects that Messier considered nuisances are some of the favorite targets for amateur telescopes today. And there's a certain period of time in late winter, early spring, where it's possible to view all 110 of these objects in one night, from dusk to dawn. And it's called the Messier Marathon. Historically, we used to have these at a club called Tuba, which was down over by Muskogee. But unfortunately, COVID kind of killed that, and there have been some other things going on where it's not, well, we won't be having them at Tuba for the foreseeable future. The owners have had a fire and other things have been going on. Fortunately, they're both okay, but for now, the Messier Marathon is going to be at our observatory. What we typically do is we get together and we set up our telescopes, and we've traditionally had a potluck, and other people have brought snacks and stuff to keep them going throughout the night. What I thought we would do is we could either do a potluck where everybody brings a dish to share, or if you want to bring your own food and snacks to keep you going throughout the night, and maybe just bring a dessert or a snack to share with everybody, that's fine. I'll have John send out an email to the membership asking what you want to do. Just kind of put it to a vote. Do you want to have a potluck, or do you just want to bring your own food, or do you want to have a dessert potluck? We talked about the possibility of the club providing drinks like bottled water and coffee, but we will need a coffee pot. We have a hot water, electric hot water kettle up at the observatory already, so we can have hot chocolate and tea. But we would need a coffee pot. We even talked about getting a Keurig up there and those little, coffee pods. But I will be organizing the Messier Marathon this year. And of course, unfortunately, I don't have any way to project my email address up there, but you can get it from John. Or if you want to write it down, it is MissTamaraM51@gmail.com. Yeah, John will send that out to everybody, but it's 2 weeks from tomorrow. John also talked about doing it on Friday the 17th if the weather's going to be bad on the 18th, but that would be a little bit difficult for those of us who work, because it would be, I think we should have a backup night other than a Friday, because it would be very difficult for those of us who are not retired yet to go to work all day and then go out to the observatory and stay up all night. There are people, people young enough to be my kids could do it, but definitely not me. So we'll be sending out information about the Messier Marathon shortly, And I hope that y'all can come. It's a lot of fun. It's a chance to, hone your observing skills, or at least your object locating skills. And it's going to be a blast. But thank you very much.
All right, that's March 18th, is that right?
Yes.
Okay, next slide.
Wait, you got a question in the back.
Okay.
Question in the back.
This is a real quick question. How long will you sit all night and how long is it going to be back?
Oh yeah, I forgot to mention, we're gonna need volunteers with keys to stay all night, because some people do stay all night. It is a dusk to dawn event. That does not mean that you have to stay all night. You can leave anytime you want, if you get tired, if you get too cold or whatever, or if you got something to do Sunday morning, feel free to go home anytime you need to. You don't have to stay all night, but I do need at least one, preferably two volunteers with keys to stay at the observatory for the entire night until the last person leaves, to make sure that the observatory is locked up.
That answer your question, Eugene?
Yes.
Shut up,
It
Siri.
doesn't matter whether you get 10, 25, or what's your record?
I don't
105?
remember what the record is. My personal best is like 95.
Okay,
Yeah,
what's
Steve's
next, Dan?
104.
There we go. Dana. Here's the laser. Much lovely assistant to help you. Here's the microphone. A lot of button does
Sit down here. Oh, I'm not hogging the clips of this record. The dome over the last several years has become progressively less reliable. It's supposed to rotate so you can look in any given direction. It's all scope-sided. Right now, if you're really lucky, you might be able to see a third of the sky, maybe on a midnight half, but it won't go all the way around. It has a friction drive that when everything goes wrong, the drive wheel will spin and the dome won't turn. So we're replacing that or supplementing it with a big gear. It's 19 feet in diameter. It was custom made, and you can see Beverly holding one of the plates there. And on the lower left corner, you've got several of this gear plates tied together. And these weird looking blocks allow the gear to sit on the structure of the dome without attaching to it. That was part of my promise that we put this thing in there and take a good look at it before we did anything that made a permanent change to the thing, in case we decided we didn't want it and we'll take it back out. So anyway, that's roughly what it is. In the bottom center picture, unfortunately, it's such a small picture you can't see what it's showing, but that's here. And then the locator blocks is lower right getting painted, and the painting blocks. We have done a tremendous amount of work. It's been a really big project. It took 5 people most of an afternoon to get the gear just hung on the frame. But the good news is the end paint up, holds it up. And that's really just an intense moment for me. Like, is this going to work? Whatever next, show it.
Next.
Here we go. The bottom right is showing a prototype gear, which will actually drive the circumference gear. Top right, we're assembling plates. We've created kind of sub-assemblies outside on the picnic table, and then we carry them up to the dome and assemble them there. We've made as big a thing we can carry up the stairs. And that's what's going on here with Skip on the right, and me in the hat. And then on the top left, you see the plates, the way they looked after they got painted. And so everything is painted because the gear is made out of steel and it will rust. And the locator blocks are temporarily wood, but there's a plan to replace them with steel. And the drive gear is temporarily made out of wood because we think it's got the wrong gear ratio, so we want to be able to change it out with something else very readily, and then long term it needs to be converted to steel also. Any other slides? No, that's not part of this project, but if you go out to the Messier Marathon, go up and look, see this thing in person, and it just takes a moment looking around and you can see what we're up to, and there you go.
They've done a tremendous amount of work on this, as you can see, both intellectually and mechanically, physically. So, thank you for all of that. The observatory was built in '92, so you do the math. It's in time to do some new things. I believe, Mr. Bragg, you are the next person. So I'll let you come up. Don't get to work anymore.
Sit down.
That's where people can see them.
The only problem is I can't see what I'm.
Go ahead, they can hear you.
Can they see the slides also?
Right now the camera's on the slides, yeah.
Okay, well, I'm gonna just stand up then, because I can't.
They can see the podium. So you're good if you stand.
So this is observing session number 5. This is about eclipses and the Saros cycle. The Saros cycle is I'm sorry?
Are you all hearing it?
Okay, how about that? The Saros cycle is a cycle that's used to predict when eclipses will occur. Next slide. So you may wonder, you know that the moon goes around the Earth, and you may wonder, well, why isn't there a solar eclipse every month at new moon? Because the moon is between the sun and the Earth, we should have an eclipse. But the moon is not in alignment with the ecliptic, which is the path that the sun appears to take. So it may pass north or south of the sun. It's tilted by 5 degrees, as you see there. Next slide. And so with that 5-degree tilt, it does have to cross the path at some point, approximately twice a year. And when it does cross the path of the sun, we call those eclipse seasons. That's the times of year when an eclipse of the moon or the sun can occur. The moon appears to cross the orbit of the sun, but orbit is close because, of course, we're orbiting the sun or the other way around. It crosses it ascending and descending, ascending and going north of the ecliptic and descending when it goes south of the ecliptic. The new and full moons near these times, usually twice a year, you may have an eclipse. Next slide. And if anybody has any questions, just yell them out. I'm going to go through this pretty fast since we have a lot on the program tonight. The Saros is determined by the orbit of the moon as it's changed by the sun. As the Earth-Moon system, there we go. As the Earth-Moon system orbits the sun is pulling on that system, and so it causes changes to the moon's orbit called perturbations. And I don't know why this is a GIF, is it not playing? We may have to put a button down here. There we go. It did something. Oh well. It's showing, okay, there we go. It's showing how it changes through the cycle. The moon's orbit will move where the eclipse season here would be at this point when it crosses the path of the sun. At this point here, but the change in the orbit of the moon occurs along the Saros cycle, which we'll talk about how long that is in a minute. But these nodes where it crosses the ecliptic drift westward due to the pull of the sun. Essentially, the sun is pulling back on the Earth-Moon system, so the moon is kind of falling backward, westward in the sky as far as where it crosses that nodal point. And the Saros cycle is the period between the cycle of the nodal drift when it syncs up with the lunar phases. The way I kind of think about this is if any of you have ever been involved with or tracked biorhythms, I'm not saying biorhythms are real, but if you've ever seen those graphs where supposedly your cycles are along different paths and at some point they all line up, that's essentially what we're talking about here. And that period is 223 months, just over 18 years. And this cycle was discovered by the Babylonians around 600 BC and ancient China probably about the same time. Okay, next slide.
That is that same angle, not degrees, something.
I'm sorry?
That perturbation, I'm looking at why does that change the angle that
We'll get to that in just a minute. It does, slightly. Okay. The ancient discovery of the Saros, there's several ways that they believe they found that discovery in different documents and different relics like this. This is a tablet with a list of the eclipses between the years you see there, and it's all from the Babylonian times. And so they believe that the cycle was already well established by that point, which was about 465 BC. Okay, next slide. And then later on, after ancient times, Edmund Halley, who's the discoverer of the comet, can you hear me now? Anyway, you probably know of him from him discovering the period of his comet that was named after him. But he also did a lot of other things. One of them was he rediscovered the Saros cycle while he was studying the moon. Astronomers at that time in history were very interested in the moon because they used the motion of the moon to determine longitude at sea. Ships didn't have GPS, obviously, or even good clocks. And so the way they determined where they were as far as longitude at sea was watching the cycle of the moon. So as he was studying the moon, he used this study that he was doing and rediscovered the Saros cycle, and he used that to predict total solar eclipse in London in 1750. And this was really the first modern, today we hear about a solar eclipse all the time. It's well established how to do it, but it was a really new thing back then. People didn't really know very well how to determine when they're big. So he was kind of going out on a limb here. And he asked for people in England to send him their observations and crowdsourced the data he got to correct the errors of the moon north. And next slide. So after he discovered that, he went through a lot of math that I won't bore you with. But what we can do today is we can actually do the same kind of thing that he did. We can track the position of the moon to determine Saros running. One of the reasons I'm bringing this up is because for those of you who do Astronomical League observing programs, the Astronomical League is having me put together a program for eclipses. Two main eclipses that are coming up, the annular one in October and the total one in April, are going to be the only ones for quite some time of the sun that are really good in America. So they're concentrating on those two. So they'd like me to put together a observing program for that. And other than just watching the eclipse, there'll be some other things to do. And one of them is to determine the Saros cycle. And the way you do that is you record the position of the moon, and you find out the period when there we go. You find out the period when it returns to the same position in the sky relative to a star, which is called the sidereal month. You determine the synodic month, which is the period of lunar phases, and that's what most of us think of as a lunar month, is like full moon to full moon, or new moon to new moon. And the next slide. And then he records some other months that are kind of like a month, but they're a little bit different. One of them is the draconic month, which is the period of the moon going through the same node, either ascending or descending node. And that's the one you really want to concentrate on if you're trying to determine the Saros cycle. And then I'm saying, Don, don't worry about what's called the anomalistic month, which is the period of the moon passing from perigee to perigee, because the perturbation effect we were talking about earlier does change the moon's orbits in other ways. It does affect that inclination a little bit. It varies between about 4 and 6 degrees. It's pretty much centered on 5 right now. And then there's also variation in perigee, which is when the moon is closest to the Earth, and apogee, when it's just as far away from the Earth as it gets. That is also affected by these perturbations, but that's not important in determining the Saros cycle. And next slide. So if you go out and record the position of the moon, either sketch it or image it, and determine the position by either your favorite software or use a star chart, record the time to the nearest minute. Doesn't even really have to be the nearest minute, just something roughly the right time. And then you find the position within, I'm saying, 4 moon widths, which should be pretty easy. The moon is not as big as it's shown on that chart there, but it's pretty easy to get that level of precision. Next slide. And then as you do that over the months, you'll track this nodal drift. And you can determine that draconic month from the motion that you're tracking. And what you're trying to find is, when does that month line up with the synodic month, which is the phase-to-phase month? Next slide. And what you'll find is, there will be a solar eclipse similar to the one that you started with after the Saros cycle, which was about 18 years, and I think 10 days, it might be 11 if there's a leap year. But the problem is that it's not a whole day. It's a third of a day. So this eclipse will occur west of you, about a third of the way around the planet. So you will see an eclipse, but it'll be far away from you and you won't notice it because you're not there. So what they did originally was they found what's called the exoligmus, which is 3 times that Saros period. After 54 years, you will see a eclipse in your region. It may not be exactly the same, but it will be close to it. And they worked backwards to find that the Saros cycle, about 3 of them happened to coincide with when they saw eclipses in their location. So all of this was all determined by people who didn't have telescopes, who had sundials for timing, who really didn't have any way of measuring the position of the moon other than looking at it and writing down or however they recorded it. And they figured all of this out centuries before Christ. And that is amazing. Yes, Dick.
There's a local eclipse that ran up the east coast of the United States.
Yes. That is the sister. And if you read the article in the newsletter, you'll see that there's in the bibliography, there's a listing there for I can't remember the title of it, but it's a government document that sort of gathered together all of the scientific experiments that were done for the government at that 1970 eclipse. And it's pretty interesting to look back at that and see how similar the track is and how they were doing sort of the same kind of things that we're going to be doing next year, with film instead of imaging and all that. Pretty interesting. John, did you have a question?
I just didn't know whether they heard about this.
No. Okay, next slide. And so there is an effect from the anomalistic cycle, which is the effect on the shape of the orbit and also the tilt of the orbit. And the main effect that we see is whether or not you have a total or an annular eclipse. The eclipse that happens in October of this year is going to be annular. This is one where you have a ring, wrong picture. You have a ring of, they call it a ring of fire. The moon doesn't quite cover up the sun, and so you have a ring of the sun around it, an annulus, so to speak, of the sun left. Or you have a total eclipse like the one in April next year, where the moon does cover it completely. And for those of you who are trying to plan, if you've never seen one, the annular eclipse is very interesting, and I'd suggest you see it. But the total eclipse is not, 5% better or whatever than the annular eclipse. It's an entirely different experience. There's utterly no comparison between the two. So put that into your travel plans, I guess. So anyway, that cycle is what determines if the eclipse is total or annular, or if it's partial. Because if you have tipped the orbit, there's going to come a point where there'll be a cone of shadow from the moon, but it won't hit the Earth because it is tipped too much. And so you'll have a partial eclipse where it'll be a sort of a bite out of the sun, but the sun won't be covered completely either in an annular or a total eclipse. So there's a lot of things. This is one reason why the study of the moon was so difficult, and took people like Edmund Halley and Isaac Newton, that level of genius to figure out all these motions, because it's a pretty difficult solution. Okay, next slide. And so this stereocycle that we're going to be looking at in April of next year, that's the total eclipse. Oh, I lost my pointer here. If you look at the stereocycle map, these are all the ones in that cycle. And this is the one of interest right here. And if you'll notice, there's another one right there. And that skips 1970. I think it's that one, or it may be the other one. I'm not sure which one of these one it is. This one? Okay. So it's even, that was even a better eclipse than we're going to get. I'm sorry, I was 4. But anyway, so you have these a cycle of eclipses that began 500 or 600 years ago, I can't remember which. And when you start off these cycles, you'll have 4 eclipses around the north or south pole. They'll be partial and hardly anybody will see them. And then at the end of the cycle, you'll have 4 eclipses in the southern hemisphere, usually partial and not very good. But anyway, the stereocycles are numbered, and all of them have been worked out. The numbering system was begun by a Dutch scientist named Vandenberg. And what I found interesting was the eclipse of next April is number 30 of cycle 139. And that is my son's birthday. And so he gets this magnificent eclipse over, Oklahoma and right around here. And then the last one in this cycle is going to be when I would have been 690 something on my birthday. And it's a really bad one down here in the southern hemisphere that nobody's going to see. Anyway. Oh, the first one was in 1501, going up here in the north. So they slowly go south, and generally speaking, the closer to the center of the Earth they are, the better they are, because you can imagine that it's that much easier to hit the Earth when you have the radius of the Earth between you and the moon. The Earth covers that distance, so it's easier to hit the center of the Earth. Okay, next slide. Okay, just a few quick mentions. It is galaxy season. We talked about the Messier Marathon. There is quite a lot of Messier objects to look at, and there's a lot of other things, especially in the Virgo region. So be sure to get out and see that if we ever get some decent weather. Next. The Starlink Generation 2 satellites have been launched. Hopefully these are going to be dimmer than the first generation. Just emailing somebody when we were walking in here about how we're going to try to look at those, and any of you are interested in observing and reporting the brightness of these things, get with me after the meeting or whenever. We're tracking the Generation 2. We were able to talk, not me personally, but the
committee that I'm on, where they want to work with SpaceX and get some changes made, and hopefully the generation 2 satellites will be less invasive, not threatening the sky, and not interfering with astronomy as much. Next slide. For those of you that look at flaring geostationary satellites, this is the time to look at them. This and yearly next equinox in October. So go out and look at those two if they're recorded up. And next, Andrew Pierce, who is a guy that uses the same remote telescope I do, discovered a nova in Sagittarius, which got up to 10th magnitude. I know this was a couple of weeks ago, and I was hoping that it was going to get brighter and we'd all be able to go out and look at it. But it's one of those really quick novas that has already dimmed it down to about 14th magnitude. So kind of missed the boat there. But anyway, it was interesting to see that amateurs are still discovering things. Okay, next slide. Oh, and I just wanted to plug Australia as an alternate. We're about to hear all about South America. If you ever want to go to the southern skies, which is like a total eclipse, something you need to do, you can see. Australia is another option, and they have great star parties there too. So just a plug for them there, and I think that's it. Yeah. So any questions? I know that was a lot of information. What?
That's your transmission fire.
Good question.
Question in the back.
Now, you mentioned the geosynchronous satellite flares. Is that like what we used to call the iridium flares? Only I suppose the iridium satellites maybe all be gone, or?
No, all the iridium flares, they have stopped maintaining their orbits. They don't flare up anymore. The geostationary flares are the ones that actually sit in place. This is like your XM radio, that sort of thing. We use it communication satellites. And around the equinox, they're always pointed towards the sun, so they get, the solar panels can get the most input from the sun for energy. And around the equinox, that means the sun is going to shine on their panels and reflect back down to you. And that happens to be the first week of March for the latitude of Tulsa. And that's when you would see them. Unfortunately, coincides with the full moon. So this may not be the year to see them, but they are pretty cool to see. They can get as bright as 3rd magnitude. You can go out and just be looking at under the tail of Leo, right around the border between Leo and Virgo, and you'll see an extra star there. That's one of those flaring up, and you'll watch it. It will get bright for about 10 minutes, and then it'll dim right back down, and you just pass through the night. Pass like a string of beads as you go through the night, as they flare up and down. So, can be pretty interesting if the weather and the moon cooperate. Okay. Any other questions? I'll let you guys know when and if they pass or say that it's okay to work on that eclipse observing program. It hasn't been approved yet. They don't do that until July. I'm pretty sure they don't have an eclipse observing program. I don't know how they would justify that. So they should pass that. And I'll let you know when that's ready to go.
Evening, everyone. I'm Byron Lavity, and I've been an amateur astronomer. Yeah, sorry about that. Byron Lavity, amateur astronomer since a small child. In my youth, since I got a driver's license through high school, summers, and I spent in the Army, which I spent part of in the desert Southwest. I spent a lot of time at 4 different observatories in the Western U.S., and I spent a week at the South African Large Telescope. But I always was interested in where all these big observatories have decided to start congregating now. And that is in the Atacama Desert and north central region of the Andes Mountains in Chile. And the National Science Foundation, through efforts by Associated Universities, Inc., decided to fund the selection of 9 people from across the United States each year to travel and see several of the observatories that were operated by NORLAB, or the Northern Optical Infrared Lab. And so this began in 2015, and in 2020, don't ask me how, but I got selected as one of the cohorts to participate. Every one of the people that went, I've been listed the ambassadors. We had Alan Strauss, had Michael O'Shea, Jason Schreiner, Derek Wallentinson, Dave Faulkner, Mark Gillette, myself, Don Davies, Chilean escort Catalina Abbas. He's from immigrated from Iran, and don't ask me to say his last name. Can't do it. And then the lead guy, Dr. Tim Spuck. We went and we all met at the Director Viacuna Hotel in Santiago, Chile on December the 9th. That next day we walked to the facilities. Went to the facilities of Associated University, Inc., the National Science Foundation, and the ALMA, forgive me, it's the team that runs the National Radio Astronomy Laboratory. All of us met at the headquarters of this facility and were introduced to several directors who explained to us where in Chile we would be going to, what the goal of the observatories, the staff, and all the entities were that ran the whole operation. And each and every observatory and entity that operates in is extremely interested in teaching the public and children about modern professional astronomy and related science. And the truth of the matter is, astronomy is really the root of all sciences. It's relative to chemistry, which planets and stars the Earth are made of. It's relative to geology. It's relative to oceanography. It's relative to physics, biology, microbiology. There's efforts made now to locate life on other planets besides the Earth. And so, very, very fascinating to learn about these things and meet these people. One thing we were taught is a lot of these observatories in the mountains that they're on are owned by land that was donated by indigenous Incan people. A lot of land, not just the mountain, but miles and miles of surrounding land. And I might mention too that the constellations, by their lore, are identified by the dark regions in between the stars instead of the shapes of animals and figures that are created by the stars themselves. For example, near the Southern Cross, is the dark llama. Behind it is a fox, and behind it is a hunter, and there's several others. So they use dark areas of the sky to create the shape of their constellations. I will go next slide that tells a little bit about Chile. Here we go. We ordered a flight on LATAM Airlines and flew 250 miles north to La Serena, Chile, where we spent the night. And the next day, we all boarded pickup trucks and drove 55 or so miles to Cerro Tololo, and it's on the eastern flank of the Andes Mountains. We put all of our luggage and everything in our rooms at Astronomers Housing. But from there, we proceeded about 6 miles over to Cerro Pachon, which is home to the Gemini Telescope, the SOARS Telescope, and Vera Rubin. The altitude of Cerro Pachon is about 8,800 feet above sea level. And you can see each observatory easily from each mountaintop. They're just separated by a valley. Cerro Pachon is home to the three telescopes I just mentioned. And first, I want to start, since we went to Cerro Pachon first, the Gemini South Telescope. This telescope presently is the largest single mirror telescope in the world at 8 meters, or 8.1 meters, and that's 319 inches. It's actually made out of 55 blocks of Corning glass that have been fused together at 1700 degrees centigrade. And after the cooling process was transported from what used to be Dow Corning, now Corning, for figuring and polishing in Paris, France, before being transported to South America. It's an optical infrared telescope that's optimized for the mid-infrared by use of laser guide, adaptive optics, and a silver mirror. How many of you are familiar with these lasers that shine out of the domes of these big telescopes? Got a couple. Well, hopefully, I'll be able to give a presentation that goes into detail exactly what these lasers do. There's more than one laser. There's a laser, sodium laser. There's a Raleigh beacon, and there's instrumentation in the image train that removes almost all of the atmospheric distortion caused by wind currents and changes in temperature in our atmosphere, and causes annoying diffraction that really inhibits the performance of these large mirrors. Due to the atmosphere, it's been determined that a very, very large telescope, 300 inch, 800 inch, 1500 inch, has no better resolving power than an 8-inch telescope. And the only way, objects will be brighter, a lot brighter, but they won't resolve any better. And the only way to achieve better resolution is through the use of adaptive optics, and they've become very, very sophisticated at this time. Now, next slide. Okay. Now, in the Gemini telescope, this is a very, very fast telescope, and it's on an alt-azimuth mount, open truss. It's a Ritchie-Chrétien design, which most modern telescopes are today. 1949, the Hale telescope of Mount Palomar was probably the last concave parabolic mirror telescope made. The mirror's made from Corning low expansion glass, and it has a suite of 4 optical infrared spectrometers located all together on the bottom so that they can quickly and easily be repositioned without having to remove and take them off of the optical tube assembly, and also helps with the balance of the telescope. The surface accuracy of the mirror on this 8.1 meter mirror across is 1/2 millionth of an inch. And I have no idea how that they are able to obtain that type of smoothness on something that large. But the technology is there and the mind power is there, and they're able to pull it off. Next slide, please. Okay, the SOAR. This next one is the Southern Astrophysical Research Telescope. It's a 4.1 meter f/16.1 Ritchie-Chrétien. It comes with several Cassegrain foci and 2 Nasmyth foci. Anybody in here have heard of Nasmyth focus points? Got one. The Nasmyth focus points are similar to that of a Newtonian, except they're midway down the tube, usually at the pivot point where the telescope rotates up and down, and you're able to attach several different instruments to these. So in combination with multiple Cassegrain foci, you also have 2 Nasmyth foci, and the Nasmyth foci also help in weight balance management, since these are off to the side on the axis where the telescope rotates. The dome's made out of fiberglass. The fiberglass reflects light and doesn't absorb heat readily and deflects it readily. So they chose, in this instance, a fiberglass dome, and probably all in all, one of the premier research instruments in the world for its spectroscopic and near-infrared capabilities. Next slide. Okay, we got the control room of the SOARS telescope, as well as a picture of the telescope itself. The little white spiky things sticking up are simply protective mirror covers that open and close like the petals on a flower. The next slide, we're going to start with the under construction Vera Rubin Observatory. It's an interesting design. First thing I thought of was a cruise ship. It's named after a pioneering Woolman astronomer who studied the rotation rates of galaxies. Go to the next slide, please. It was previously referred to as the Synoptic Survey Telescope, or Large Synoptic Survey Telescope, and synoptic simply means large or large area, a large area view. This telescope will have the largest imaging sensor ever constructed. It'll be 24 inches by 24 inches, and it will be, let's see, trying to see how many gigabytes, 8.4 meter, well, the camera, if you have a 35 millimeter camera, that's say 36 megapixel. This thing's like 3.2 gigapixels, so 3,200 megapixels compared to your 35 millimeter camera. It gives you an idea to the enormity of it. And its mission is to photograph the night sky, the entire night sky, every several days. The large image sensor gives it the ability to photograph a 3 to 3.5 degree field of view. And it's designed to locate objects 300 meters or larger in the solar system, and primitive Kuiper Belt items. And the reason it's searching for these is they're looking for things that pose a hazard to Earth, and it's designed to detect and send out the data once every 60 seconds, and it will create an alarm if there's a change in brightness or movement in any of the stars in the sky. Just
I was just gonna say, the Vera Rubin telescope is the point that people are looking at the starlings, whether they're looking at the sky or not. Vera Rubin telescope is one telescope that really concentrates on it. Byron was saying, take these pictures of a large area of the sky, and you get a bunch of streaks from starlings from the satellites across the river, and think that it's an incoming asteroid or whatever. It really will ruin the whole work of this possible several tens of millions of dollars.
right. The Simone family donated 25 million. Bill Gates donated 10 million, and National Science Foundation donated 3.5 million. So it's 5.5 million. So it's $35.5 million instrument, and it's gonna send out 10,000 alarms each night. So satellites passing across this wide field is going to wreak havoc on it. And I don't know yet how they're going to figure out a way to subjugate this type of annoyance that's going to really mess up the data. Yeah, back to the sensor. It's a 3.2 gigapixel, which is 3,200 megabytes. It's operated under management of Associated Universities for Research in Astronomy, and it will catalog 90% of the near-Earth objects that pose a hazard, and it will also find some 10,000 primitive objects located in the Kuiper Belt. Let's see what I haven't done over here. It's also going to try to detect thousands of supernova, both nearby and at large redshift, and by measuring the distribution of dark matter through gravitational lensing. The Large Synoptic Survey Telescope makes no attempt to compensate for dispersion in the atmosphere, as such corrections would require adjusting an additional element in the optical train, and would make it difficult for the camera to be able to take 20-second exposures, which what it does. It takes 20-second exposures. It allows 5 seconds to move to a new position, settle, and then start another 20-second exposure over and over and over again. So, the image quality will be degraded slightly, but not enough to, have any real impact on what it's designed to do. So, project numbers. Now, Dan, you're on the right path. Each exposure, as I explained, is 20 seconds. There's 189 charge coupled device detectors, each one 16 megapixels. And I already told you about the alerts. 10 million alerts will be generated per night. So you're gonna need, and they have a massive supercomputer to crunch that many alerts and to determine the origin, what they are, and where they are. Next slide. The mission. Reuben will serve 4 main categories of users: the general public, formal educators, citizen science principal investigators, content developers at informal science education facilities, and the Reuben Observatory will partner with Zooniverse for a number of their citizen science projects. Zooniverse is geared towards youth. So, as you can see, they're really intent on helping the public. From Cerro Pachon, we went back over to Cerro Tololo, and I really love this complex. There's over 40 different instruments located on the mountaintop. Here's the Victor Blanco telescope. It's a 4-meter. That dome is actually not aluminum. That's the color of the specialized paint. It tends to absorb heat readily during the day, but it disperses it quickly at night. That's what they're interested in. Then we have the SMARTS Consortium, which is a small to medium aperture research telescopes. This is a 1.5 meter telescope. This one is a 0.9 meter telescope. This is a 1.1 meter telescope. And this is a Schmidt camera. This telescope's operated by the United States Naval Observatory, and this one's operated by the one of the universities in Asia. I can't remember which one. These 2 towers are scene monitors. The 4th member of the SMARTS Consortium is a 1.3 meter telescope, and it's located down here where it can't be seen. Yeah. The name of the paint that coats the dome is called titanium oxide. Cerro Tololo is located in the Coquimbo region of northern Chile. The 4-meter telescope is called the Blanco telescope, and it's named after Victor M. Blanco. In 1959, he discovered a group of galaxies that was named after him. And him and his wife worked together to discover or pioneer research in stellar populations within the center of our galaxy and imaginary clouds. And Victor Blanco was the 2nd director of this telescope, which went into operation in 1973. Okay, yeah, there's a picture of the Victor Blanco 4-meter telescope, and if you ever get a chance to go to Kitt Peak to the Mayall 4-meter telescope, this is an identical twin. They're exactly the same design, same size, same everything. And it was just easier for them to manufacture this since they had have all the fabricated prints, designs, methodology and everything, and it just didn't have to go back to the drawing board. They assembled it and took it, put it into place, and the 4-meter mail went into operation the very next year, 1974. The main purpose of the Victor Blanco telescope is the use of the dark energy camera, and it's currently the main research instrument. And the DCAM is a CCD imager mounted at prime focus. Major components are 62 science charge coupled devices, 8 wavefront CCDs, and 4 guide CCDs with amplifier. This camera found 12 more Jovian moons, a giant comet in the outer solar system, the fastest orbiting asteroid, an extreme dwarf planet, and new stellar streams confirming the melting pot history of the galaxy. Now, the SMARTS Consortium, I already mentioned those and pointed them out. There's 4 different ones. There's a 1.5, a 1.3, a 1, and a 0.9. The larger 2 are open truss cassegrains. The smaller 2 are closed tube cassegrains. Next slide. Tenet telescopes. There's a large number of Tenet telescopes ranging in size from 0.4 meters to the last of the SMART Consortium, 1.6, which can be seen to the far right of the picture, silver side and silver dome. They're part of a network of 3 other telescopes dedicated to detecting exoplanets, and all of the remaining telescopes are shared by schools, universities, and even individuals. They're ancillary telescopes. From there, we flew further north. Next slide, please. Up to the Atacama Desert, which was fascinating. The morphogeography there is very, very similar to Mars. As I was looking around, I was thinking of Spirit and Opportunity, and was amazed at some of the places that look strikingly similar. And at an undisclosed location in the Atacama is actually a training ground for astronaut geologists should the time come when they're able to explore Mars. They take samples here, learn to sample, and all that. So we went and stayed in the small town of San Pedro de Atacama, and from there we drove up north to through the desert to the Atacama large millimeter, sub-millimeter lunar telescope array. Atacama Desert, as I said, is striking, similar to Mars. And on the east side, there's a ridge of mountains. On the right side, it's just row after row of volcanic cones. Some of them have cone tops over 20,000 feet above mean sea level. And we stopped along the way to visit a place called Flamenco, and it's easy translation meaning flamingo, as there's flamingos there, and it's a salt flat made of halite. Halite is salt. Salt is sodium chloride. So why we need to call salt sodium chloride or halite, I don't know. It's a science thing. So pick your pleasure. what are you gonna say? Honey, bring me some halite. I need to season my potatoes. All right. So, okay, there's a low site at the Atacama Desert that houses all the offices and the administrative and maintenance facilities, as well as the transporters that move the radio telescopes up and down the mountain. And there's transporters, several of them. They have 28 wheels, and they carefully pick these telescopes up with grab arms on both sides. The width of them spreads in and out, and they have 28 wheels, and they travel at 5 kilometers per hour. There's a driver, and then there's a guy that sits, and his job is to have his hand near a red button in case something happens to the driver that he becomes incapacitated. The second person in the vehicle slaps the red button and the vehicle stops. So it takes more than a half a day to a full day to get one of these dishes up to the high side at 16,400 feet. And the roads in between the dishes are made of highly compacted fine gravel to reduce or minimize vibration, because if you used asphalt or concrete paving, the vibration would be exacerbated. So there's no rails or anything to move this stuff along. But these antennae are spreadable from a central point out to 16 kilometers, which makes it one massive radio telescope array of 66 antennae. 54 of them are 12 meters in diameter. 12 of them are 7 meters in diameter. They're operated by Japan, Europe, and the United States. And we're on slides. Okay, can we go back to the dishes? Okay, yeah, I just got that. There you go. Okay, next one. All right, go ahead, next one, please. Okay. Okay, the difference between a radio telescope and an optical telescope is the wavelength of the radiation collected. An optical telescope is going to collect the visible spectrum into the infrared, whereas radio telescope expands way further deep into the infrared, into the radio waves, and its ability to detect radiation is 1,000 times larger or longer in wavelength than what you pick up with an optical telescope. A lot of people think that you have an array of 66 dishes spread over 16 kilometers, it works like one giant dish. Well, it does, but it's not in the way you might think. It's not one big dish kind of working together. There's a phenomenon called interferometry. And interferometry is, whoever came up with it was brilliant, because what you do is, in optical telescopes, you'll make an interference pattern with mirrors and lasers. In optical train, in radio interferometry, the distance between the antenna, the light, or the waves, the radio waves entering these telescopes is separated by a certain number of dishes. The closer they are together, the quicker the signals arrive at each dish, but they're slightly different, and we're talking nanoseconds. But their computers at the low side are able to tell the difference, and this creates a smudge in the image that they're taking. And the smudge is actually a whole bunch of pixelates, and then the computers analyze each of these pixelates individually and reassemble it, and they produce a much, much sharper and more detailed image of the object being studied than if the interferometer wasn't used and it wasn't smudged out in the first place. It's smudging it out in speckles, and each speckle is analyzed. And it's not just the separation of each dish that affects the time of arrival of the signals. It's also the angle of the dish, making a separate separation, and it even goes down to the length of the fiber optics cables intertwined between all of them. And in order to computate the speed of light signals, even at 16 kilometers, you have to have technology that's able to measure that very, very short time spread. You have a bank of computers in a room that is cooled to 35 degrees Fahrenheit, and the bank of computers has an equivalent memory capacity of 3,000 desktop or laptop computers. And so we had a great time, saw the radio telescopes, learned what they did. I'll talk about adaptive optics later, and we're going to have a planetarium show that's going to do a better job than I did talking about this and filling in the blanks on anything I missed. So I did the best I could. Thank you very much.
We'll let Byron get up and kind of get organized. I would suggest if you're like me, you might want to stand up, stretch your minutes too. So what's it gonna take to bring up the dome show?
Nothing, it's ready.
Do we have time for like a 5-minute break?
I can give it to you, yeah.
Are we all right, everybody? Let's do that. Let's quick break, that stretch.
Just 8:30. We usually go to 9, so time to break.
Yeah, I think so. No, I think it was, I have it at, no, I still have your PowerPoint up.
When he was talking, what did I do? Talk
Your PowerPoint's still up. It shows 39 minutes. Your
That's
PowerPoint.
about, I allotted myself 30 minutes. You did a really good job keeping the slides up.
Yeah, just keep it with you. I mean, you made it easy to do because I just read the next slide and you just went.
My brain was turning. I kept getting to see next.
Cool.
You were on
I was
top.
already, I was on you. I was on you.
Appreciate it.
That's awesome, seeing all that big glass, huh?
I didn't know this, but all that sodium comes from billions
All right, well,
of
let's
sodium
let Dan run
dust
the
particles.
show.
We'll go into that. Yeah. I got me on a roll.
Yeah.
Sure. Got everybody?
Think so.
As an astronomer, I always marvel at the night sky. It's beautiful, of course, but light from the universe also helps us unlock its secrets. My name is Bárbara Rojas Ayala, and I study stars. We have learned that almost every star we see hosts one or more planets, and we're finding more planets all the time. So for me, the night sky is filled not with distant, lonely stars, but with countless families of planets. I want to share some of these family stories with you, where they come from, how they take shape. But I also want to introduce you to where I come from. A place where astronomers study the sky, with the help of amazing technology and even more amazing people. A place where people have experienced a strong connection to the night sky for millennia. I want to introduce you to astronomy in Chile. Chile lies on the west coast of South America, a long, narrow, mountainous country. The Pacific Ocean lies to the west, the towering Andes Mountains to the east, and the Amazon rainforest to the north. Chile is perhaps the best place in the world for observational astronomy because of its special climate. The Andes block rain clouds from the east, while currents in the Pacific Ocean bring cold waters north from the Antarctic. Along the Chilean coast, the air temperature drops, and as the cool air sinks, it loses its moisture. These factors combine to create stable dry air over Chile's coastal mountains with few clouds, perfect conditions for astronomy. Many major telescopes dot Chile's mountainous terrain. We will visit just 3. These observatories are looking at places in our solar system and beyond to help astronomers understand where planets like ours come from. Standing on the side of this mountain, you can understand why it was named Cerro Tololo, which in the Aymara language means at the edge of the abyss. Cerro Tololo Inter-American Observatory is home to dozens of telescopes. Let's take a look at the largest, the Victor M. Blanco telescope, with a primary mirror 4 meters in diameter. Astronomers designed this telescope to observe the same kind of light our eyes can see. It's an optical telescope. Light enters the large opening and bounces off the giant mirror. It's the first thing the light hits, so we call it the primary mirror. The bigger the mirror, the more light it can collect. So astronomers like to build large telescopes to gather as much light as possible. The shape of the mirror focuses light on a giant lens, more than a meter across. That lens is part of an amazing instrument called the Dark Energy Camera.
The Dark Energy Camera has 62 science detectors, one of the biggest cameras in usage in the world right now.
Marco Donati is the first of several people we'll meet who keep these observatories running. As an electronics detector engineer, he's responsible for what happens inside the instrument.
You need to be very careful that they are clean all the time, because otherwise you have all sorts of stuff deposited in the surface, and the surface is especially coated. Basically, we want to avoid any dust particles. So in the clean room, we have a controlled environment. We can control the amount of dust inside by basically having filters and positive pressure that keep the dust out. All the light that the telescope gathers goes to a single point, basically. At this point, you put the detector. So the detector you put there depends on the science you want to do and the instrument, a lot of factors.
Once the instrument is out of the clean room and mounted on the telescope, other team members help make the observations.
My name is Jacqueline Zero, and I work at Certololo Inter-American Observatory. My position is night assistant. This means taking care of the instrument and having the telescope ready, taking calibrations, and making sure that everything is working fine. And during the night, operating the telescope, which means moving the telescope to the position that the observer wants, and making sure that everything is working correctly. What I really like is to learn in general how the telescope works, how it takes data, and all these different systems that are interconnected and that, accomplish such a huge task, and, all the engineering involved. It's amazing.
Let's hear more from Kathy Vivas, a Venezuelan astronomer living in Chile.
I am part of the support team of one instrument in the Blanco telescope, the Dark Energy Camera, which is a wonderful instrument. It's special to make surveys to cover large portion of the sky. As part of the support team, we make sure that the camera is producing science quality data that is ready for astronomers from all around the world to come and do their science projects with the telescope, and that they can achieve their science goals with this instrument.
The Dark Energy Camera was designed to peer into the farthest reaches of the universe. But because it can observe a large portion of the sky, it also helps us search for objects much closer to home. Leaving Earth behind, we see the orbits of planets around the Sun. Mercury, Venus, Earth, and Mars. Jupiter, Saturn, Uranus, and Neptune. But our solar system includes many other objects, not just planets. Astronomers have used the dark energy camera to find numerous small, icy bodies in the outer reaches of the solar system. We have tracked thousands of these objects, which reside far away from the Sun, past the most distant planet, Neptune. They make up what's called the Kuiper Belt. Billions of years ago, everything we see here likely revolved in the same plane. But the massive planet's gravity tucked the lightweight Kuiper Belt objects into different orbits. They now travel far above and below the plane of the planet's orbits. Each tiny icy world we discover helps us answer questions about the history of our solar system. What did it look like billions of years ago when the planets were taking shape? We can't go back in time, but we can observe other planetary systems in the process of forming. This work requires our most powerful telescopes, so let's return to Chile. We're heading to a mountain called Cerro Pachón. Only about 20 kilometers from Cerro Tololo. Here we find the Gemini South Observatory, which began viewing the sky in 2002. Inside the dome, we can see the giant telescope with a mirror more than 8 meters across, more than twice the diameter of the Blanco telescope. This giant mirror must remain highly reflective, which means it needs cleaning every week. Such a big job requires a lot of teamwork.
My name is Vanessa Montes. I'm an electronics engineer. We have different disciplines like optics, mechanics, electrical, software also. We all work very well. It's a lot of team effort and a lot of collaboration between everyone. And I think that that's very positive. The more you can encourage people to participate more creatively in the different projects that we do, it's a more collaborative work environment.
Cooperation on Gemini extends around the globe. Astronomers rarely travel to Chile to use the telescope. Instead, they telecommute. Here, in the Gemini Base facility in the coastal town of La Serena, nearly 100 kilometers from Cerro Pachón, technicians can operate a special instrument that looks at young planetary systems, called the Gemini Planet Imager, or GPI. Almost 10,000 kilometers away, at Stanford University in California, observers see the same displays and guide the work with GPI. Astronomers need somebody they can trust on the other end of the line, and that's where Alicia Shugart, Science Operations Specialist, comes in.
We operate the telescope at night. We take data for the astronomers who have all contributed proposals for science. I really enjoy observing. I think about it as if these photons that literally are billions of years old are arriving and I'm seeing them for the first time.
Not all photons are billions of years old. Many were created more recently, closer to home. Light detected by GPI reveals what happens when planets form around nearby stars. We can imagine traveling to one such place, so far away that its light takes more than 60 years to reach us. This star is more massive and much brighter than the Sun. The star and its planetary system are less than 30 million years old, mere infants compared to our own middle-aged solar system. Dust and debris form a disk around the star. Some tiny objects in this disk will end up like our Kuiper belt, icy bodies at the edge of the system. GPI allows us to peer into the center of the disk. Astronomers then use computers and the laws of physics to simulate what might be happening. We have discovered one giant planet, more than a dozen times more massive than Jupiter, whose gravity has sculpted the dusty disk into a warped spiral. Could something similar have happened in our solar system billions of years ago? For the next part of the story, we must now travel much further north in Chile, to the Atacama Desert, one of the driest places on Earth. Home to a collection of 66 radio antennas, the Atacama Large Millimeter Sub-Millimeter Array, or ALMA. The skies of the Atacama Desert are famously clear, and people have observed the sky from here for millennia. David Barrera is president of the indigenous community of San Pedro de Atacama.
I feel that the cosmos works with me. It works with you, with humanity. It is part of our life. We humans are nothing compared to what the great cosmos is. That is why we are part of the cosmos. We work together. We make up a single unit. That is the marvel of the human understanding. Alma has been a respectful neighbor because it has asked what is the ancient wisdom of the native people in regard to the cosmos. And Alma's invitation to the indigenous community is in some way to unite scientific knowledge with indigenous knowledge.
Astronomers have come to this unique spot on Earth to build an array of telescope antennas that benefit from the clear, dry skies 5,000 meters above sea level. These giant antennas work together, like a single, enormous eye observing the sky in unprecedented detail. And they can work both night and day. Each dish weighs about 100 tons. And they need to move from place to place, both to make different kinds of observations and to receive maintenance when needed. Alfredo Elgueta is one of only 4 people trusted to operate the transporters that move the telescopes.
The transporter has just one basic work that is designed to do, and it's move this big radio telescope from one point to another. When you're doing the maneuver of trying to load the antenna or unload the antenna, you have to do it with the remote. But when you're doing the translation from one point to another, you have to do it from the cabin. So every time that an antenna needs like a big fixing or anything, we try to bring it down, but it takes a lot of coordination to do that. It takes around 5 hours, driving 5 kilometers per hour.
Once the antennas are in their correct locations, They collect a huge amount of data, and they work as a network. Data from each antenna is compared to data from every other one. Celia Verdugo, an astronomer and data analyst, collects and studies these observations for astronomers from Chile and other parts of the world.
The kind of light we are collecting from the sky is a light that is emitting in radio wave shape. See? We are looking at the parts of the universe with the lowest temperature, and because of that low temperature, they emit their energy through radio waves. We collect that signal, and from that, we can get either spectral information, or we can also get images of the source we are observing. And we're taking data for projects that are breaking the limits of what we know, going beyond the limit of our knowledge. That is really fascinating. Yeah.
One of the ways ALMA has revolutionized our view of the universe is by giving us a close-up look at young planetary systems. Here, we are seeing not just the leftovers of planet formation, but the actual disk of material from which planets take shape. This is ALMA's image of BDS-70, a very young star, less than 10 million years old. Its debris disk looks more like a ring of dust surrounding the star, with a large gap where at least one Jupiter-sized planet is forming. That planet has a small disk of its own, where moons could be forming around it. Here, we're seeing the results of a computer simulation, which we can compare with data from ALMA and other telescopes to help astronomers understand how planets grow. Perhaps our solar system looked like this billions of years ago, a family of planets taking shape. Pioneering work in astronomy requires investing in the next generation of telescopes. When completed, this telescope will observe the entire visible sky every few nights. It will generate 20 terabytes of data each night, twice as much as the Hubble Space Telescope generates in a whole year. All the data will be made freely available to the world, enabling anybody to make the next great discovery. The future of astronomy lies in all our hands. That's why I enjoy meeting with students of all ages. I hope some of them will grow up to work with me at one of Chile's great observatories or elsewhere in the world. All of us you met today come from different backgrounds with many different talents and skills to contribute. We invite everybody to look, to learn, and to enjoy astronomy. We hope to share the wonder of the sky and the excitement of discovery with the whole world. If you'd like to meet more amazing people and hear more stories about big astronomy in Chile, visit bigastronomy.org, where you will find live conversations with observatory staff, exclusive behind-the-scenes content, and educational activities.
All right, Mr. Dan, can we have some light? Right. very much for coming. If you're interested in the Messier Marathon, there's a sign-up sheet in the lobby, or you can catch Tamara over there in the corner. There she is back there. Anyway, thank you very much.
Beautiful South African music take us out. Oh, South American. Glad I said that.